Complex numerical problems were being solved in Mesopotamia centuries before formal algebra existed. In the cities of the 3rd and early 2nd millennia BCE, expanding administrative systems generated sustained demands for calculation. Agricultural production, land allocation, taxation, labor obligations, and exchange required stable methods for transforming quantities. Clay tablets inscribed in cuneiform fixed these transformations in material form. Within this environment, a mathematical practice emerged that relied not on axioms or deductive demonstration, but on ordered procedure. This is before logic, a history of rules before they were written. The scribal schools of the Old Babylonian period trained students through structured exercises preserved on surviving tablets. Problems appear in standardized verbal formats involving fields, canals, bricks, silver, and grain. Solutions are presented as sequences of operations. They do not include general demonstrations or explicit theoretical justification. Instead, they specify what is to be done in a determinate order to obtain a quantity that satisfies the conditions of the problem. Each operation constrains the next. When executed according to the prescribed sequence, the result conforms to established expectations. Babylonian mathematics operated within a sexagesimal place-value system. This positional structure allowed compact notation and facilitated division through reciprocals. Numerous tablets preserve tables of reciprocals, squares, cubes, and related values. These tables functioned as computational infrastructure. When division by a number was required, the reciprocal could be retrieved and multiplied. The procedure reduced variability in calculation and supported reproducibility. The tables did not articulate theoretical foundations. They enabled consistent execution across repeated contexts. The properties of the sexagesimal base influenced which magnitudes could be handled directly. In a base of 60, many devices produce finite reciprocals. Numbers that possess such reciprocals were considered regular within the computational tradition. Irregular numbers, whose reciprocals did not terminate in the sexagesimal system, required alternative treatment. The existence of reciprocal tables meant that operations were structured around the numbers those tables contained. When a magnitude did not align with a regular form, it was often approximated or transformed into a computable equivalent. In this way, the organization of the tables shaped the range of operations that could be performed efficiently. The structure of the number system therefore conditioned practical solvability within the scribal curriculum. A substantial group of tablets concerns problems that modern historians classify as quadratic in structure. A typical example describes a rectangle for which the area and the difference between its sides are known. The task is to determine the lengths of the sides. The solution proceeds through a fixed sequence of transformations. The scribe is instructed to take half of a given magnitude, multiply it by itself, add the result to another magnitude, and then extract a square root. The procedure can be understood as a geometric recombination of quantities arranged so that an unknown becomes accessible through measurable steps. No general symbolic formula is stated. The narrative format encodes a template. When a new problem matches the same structural conditions, the same sequence can be applied. This orientation toward procedure extended to geometry and measurement. Problems involving irregular fields or volumes were reduced to combinations of standard shapes. constants were supplied within the tradition of practice. In certain cases, approximations were employed. The values used do not correspond to later exact formulations, yet they were adequate for surveying and construction. The objective was operational stability across administrative tasks rather than theoretical completeness. The absence of explicit theoretical commentary in the mathematical tablets has been interpreted in different ways. Some scholars suggest that conceptual understanding may have existed without being recorded in surviving documents. Others maintain that the corpus reflects a mathematical culture oriented primarily toward effective procedure rather than abstract explanation. The tablets themselves preserve instructions and results, not reflections on foundational principles. Surviving sources indicate that correctness was determined by conformity to accepted procedures and agreement with tabulated values rather than by deductive proof. The structure of these procedures is sequential and constraining. Each step conditions the next. Errors introduced early in the sequence affect the final magnitude. Reliability is a function of procedural adherence. Scribal training appears to have emphasized repetition of standard forms and internalization of established sequences. Mastery consisted in recognizing structural similarity between problems and applying the corresponding template without deviation. The authority of the method derived from institutional continuity and accumulated precedent. Certain tablets, including the well-known Plimpton 322, contain numerical lists arranged according to specific relationships. The precise function of this tablet remains debated. It may have served as a pedagogical resource or as part of a computational exercise. The numerical distribution has been interpreted as relating to right triangles. Whether these relationships were conceptualized within an explicit theoretical framework comparable to later geometric systems is uncertain. The historical record supports the conclusion that the numbers were generated and organized within an established computational practice. Babylonian mathematics demonstrates that results can be stabilized without formal axiomatization. Procedures were transmitted across generations through scribal institutions embedded in temple and palace administration. Economic and legal systems required dependable calculation. In this setting, the value of a method lay in its reproducibility. The method did not require articulation of general principles in order to function within its domain. Its authority rested on established use and the stability of its output over time. The language of the problem texts reflects this orientation. Instructions are expressed as commands to take, multiply, add, subtract, or extract. The grammar encodes transformation rather than explanation. The steps are finite and determinate. When followed as prescribed, they yield a magnitude that satisfies the problem's conditions. The sequence itself constitutes the structure of reasoning. The tablet records not only quantities, but operations applied to those quantities. In this way, calculation becomes externalized and materially fixed. Limitations of the surviving corpus must be acknowledged. The tablets that remain represent only a portion of what once existed. They derive primarily from particular sites and periods, especially the Old Babylonian era. Practices may have varied across regions and centuries. The absence of theoretical exposition does not demonstrate that no reflective activity occurred. It indicates only that such reflection is not preserved in the extant mathematical tablets. Interpretations must therefore remain constrained by available material evidence. Despite these uncertainties, the procedural character of the corpus is clear. Knowledge was organized around reproducible operations supported by tables and training. The system did not depend on deductive chains derived from stated axioms. It depended on the stability of method within administrative and educational institutions. Calculation was detached from immediate physical measurement and embedded in symbolic procedure. Marks impressed in clay encoded sequences that could be executed independently of the original situation. Babylonian algorithms were not presented as universal theories. They addressed recurring classes of problems encountered in administration, surveying, and exchange. Their generality was embedded in template structure rather than abstract formulation, a procedure applied wherever a problem matched established conditions. Recognition of structural similarity guided its use. Abstraction operated implicitly through repetition of form rather than through explicit general statements. Over time, procedural knowledge acquires durability when embedded in institutions. The clay tablet serves simultaneously as record and instruction. It fixes numerical relations and preserves transformations. Through this preservation, reasoning becomes transferable across generations. It can be transmitted, corrected, and standardized without requiring articulation of underlying theory. Such procedures operated without explicit axiomatic structure and without formal proof. In the next episode, we will examine Egyptian optimization and engineering practices that achieved large-scale construction without formal proof.